Wow, I'm prepared.
Okay.
Question.
So, welcome everyone. So today's speaker, I think, does not need too much introduction to everyone, but Liying Chen is Project Scientist 3 here at HAO, and she holds a Bachelor of Science in Atmosphere Physics from Nanjing University and Master's in Atmosphere Physics from Chinese Academy of Science, and then she did her PhD in meteorology and atmosphere science from Penn State. And her research focused on the physics and dynamics of mesosphere, thermosphere, and ionosphere, with an emphasis on understanding their variability and coupling processes. And today she will present on the dynamic ionosphere thermosphere system variability from minutes to decades.
Okay, thanks, Nick, for the introduction. And okay, so for this online, can you hear me clearly?
You're good.
Okay, all right. Okay, so thanks for coming. So today I will talk about the dynamic ionosphere thermosphere system variability from minutes to decades. So the ionosphere thermosphere is highly dynamic with very complicated variability. Today I will use timescale as a thread to talk about some of the variability. So this is the ionosphere thermosphere system. It is a system within the Sun-Earth system, and it is located around 100 kilometers and 600 kilometers. It is where the low Earth orbit satellite, the LEO satellite flies, and where the GPS signal and the HF radio signal transmit. The ionosphere system, the IT system, is an externally driven system. It has three types of external forcing. The first is the solar irradiance in the wavelengths of X-ray ultraviolet, extreme ultraviolet, and far ultraviolet. And the second type is the aurora energetic particle and electromagnetic energy as a result of the interaction between solar wind and magnetosphere. The third type of forcing is from the lower atmosphere, including tides, gravity waves, and planetary waves. So here shows the IT system composition, altitude versus number density. On the left is major ions, including NO+, O2+, and O+, and electron. And to the right is the major neutral species, including O2, and A2. And so the IT system consists of partially ionized plasma, meaning that it is in charge neutrality. In charge neutral, and which means the sum of ion density equal to approximately equal electron density. And also the IT system is weakly ionized. Even at F2 peak here, ionosphere F2 peak here, the neutral density is still about 1,000 times of the plasma density. And driven by this external forcing, a number of internal processes take place within the IT system. This including photoionization, photodissociation, and ion-neutral coupling, which manifest in dynamics, ion drag, and in electrodynamics, for example, neutral wind dynamo, and in energetics, including through heating and plasma neutral rotational heating. And then there's a wave-induced heat and momentum transport and heat conduction from the higher altitude to lower thermosphere, where the radiative cooling release the energy, and together they balance the IT system energy budget. And driven by the external forcing and these internal processes, IT system undergoes very complicated variability, which here can be sorted into space weather and space climate. Space weather including short-term variability driven by solar flare and geomagnetic storms. And then there's day-to-day variability, which can be driven by both geomagnetic forcing and the lower atmosphere wave and tides. For space climate, there's solar rotational, seasonal, solar cycle, and multi-decadal. And this variability can be sorted in time scale from minutes all the way to greater than a solar cycle. So why do we start the IT variability? So first, it's a fundamental science. It's the basic chemical, thermodynamical, dynamical, and electrodynamical processes. And it's about the energy and transport and dissipation through cross-domain, cross-scale coupling within the geospace. And it is about finding the physical drivers behind the ionosphere irregularity and the thermosphere density variations. which are very essential, which affect essential space technology, including satellite tracking, space debris population and traffic management, and global navigation satellite system and GPS signal positioning accuracy, and high frequency radio signal propagation and communication. So understand the IT variability, support the fundamental science and the predictive goal in the new space solar and space physics decadal survey, and it's about safeguard our only known habitable local cosmos, the Sun-Earth system. So my research focused on understanding IT variability and its origins, and looking at how small and the origins of small and large scale plasma irregularity and neutral density variation from impulsive to multi-decadal variation. And so it involved ion neutral coupling, and it involved cross-domain coupling. And for example, the IT system coupling with the low atmosphere is about looking at momentum, term, and energy from the low atmosphere waves, how they impact the large scale circulation and composition in the IT system. And this region, this coupling region happens in the altitude region about 80 to 120 kilometers. And in our community, some call this Ionosphere because it is historically ignored due to the challenging in both observation and in modeling. From observation, this altitude is too high for balloon, and it's too low for most satellite. And from modeling, this is where the lower boundary of most upper atmosphere general circulation locates. And this region is also where the waves interact with each other, interact with the inflow, and the waves breaks and dissipates and deposit their momentum and energy there. And this region has a very strong chemical, thermodynamical, and dynamical gradient, especially in the vertical. And this is also where the mass pulse, pulse, and the turbo pulse locate. And the coupling between low atmosphere wave and the IT is multi-scale. It's from small scale to mesoscale to large scales. It's very complicated. And so for the methodology, I mostly do modeling, which involves some coding, mostly associated with adding some capabilities, such as diagnosis capability, sensitivity test, and the parameterization or in model improvement. But mostly it's model simulation and the model result analysis, and which would also involve data analysis, both space-based and ground-based data. So today's topic, so we were looking at variability related to IT coupling with solar wind and magnetosphere. We will focus on solar flares and focus on day-to-day variability driven by geomagnetic forcing, and also looking at variability related to IT coupling with the low atmosphere. And for this, we will focus on seasonal scale variation and meridional circulation. And lastly, we will looking at IT trends. And the contents of today's presentation will focus on research done by my postdoc, my graduate visitor program students, myself, and the close collaboration with colleagues at HAO and outside HAO. So first, solar flares. So solar flare is a sudden burst of solar radiation from sun's chromosphere, and due to a rapid release of magnetic energy that is stored in the solar atmosphere, and it takes about 8 minutes for the solar flare reaching the upper atmosphere of the Earth. And it causes sudden enhancement of photoionization and therefore sudden enhancement of plasma density and heating in the IT system. So here we're looking at flare impact in the ionosphere, looking at the enhancement of TEC, which is a total electron content. It's a vertical integration of the electron in vertical column. So on the left, this is from GPS observation, right? It's a time GCM observation, model simulation. And the top panel is at 11 UT. And this is right before this X17 flare occurred. And at this middle panel is at 1110. This is the peak of this flare. And then this lower panel shows the enhancement of the TEC to 30%. So you see that it only takes minutes for this flare from start to reaching the peak, and it usually take about 1 hour or sometimes even less for a flare to decay. And this sudden increase in plasma density impact GPS and high frequency radio signal propagation. And this is the same flare, but the impact on the neutral temperature and mass density at 400 kilometers. 400 kilometers is a typical low Earth orbiting satellite altitude. That's the International Space Station altitude. And so for this flare, the neutral temperature increased about 85 K under the background of about 1000 K, and the mass density increased about 20%. So this sudden increase in mass density in the low Earth orbit environment will cause a sudden change on satellite drag. And then the solar flare effect is not just limited in the IT system. It also has feedback in the magnetosphere. So this is the impact in the magnetosphere. We are looking at the magnetospheric convection. This is with the flare, or this is to a flare more recent solar flare. This is a with flare, this is without flare, and this is a different. So you clearly see there's a significant impact on magnetosphere convection. And this change in magnetospheric convection will change the energy flow from magnetosphere to the IT system in both aurora particle precipitation and electromagnetic energy. So here, these are the three usual suspects that will be involved in magnetosphere, ionosphere, solar sphere coupling. First is the Patterson conductance. So at the flare peak, the Patterson conductance increased about 100%. And this is the field aligned current increase about 30%. And then this is the convection electric field. So the cross-polar cap potential decreased by 12.5%, and the Joule heating decreased by 50%. So solar flare reduce the effectiveness of the transfer of electromagnetic energy from solar wind and magnetosphere to the thermal and the kinetic energy in the IT system. And the geo-effectiveness of flare is highly depend on the location of the solar flare on the solar disk. So the top panel shows two solar flares in tailwind storm period in 2003. It's so-called EUV image. So to the left is a smaller magnitude flare, but it's on the disk, and the right is X28, a larger magnitude flare, but it's on the limb. And the lower panel shows the chamber neutral density response. So you see the neutral density response to this smaller, but on the solar disk flare is larger than the X28 flare. And the reason is solar atmosphere is optically thick to EUV. So if a flare is on the limb, then the EUV need to travel longer distance of the solar atmosphere. So by the time you reach the Earth's upper atmosphere, actually there's a less UV enhancement. So it is less geo-effective. So move on to day-to-day variability, we will focus on nighttime ionosphere. So this is a nighttime ionosphere observed by NASA Boulder. So we are looking at 3 consecutive days during November of 2021. So the first day we see plasma bubble. This plasma bubble is the one that will cause scintillation to both GPS and also impact the GPS signal and also the high frequency radio signal. And the second day is you have seen less plasma bubble, but the 2 plasma crest merged together. And the third day is, again, there's a long bubble and the crest becomes even brighter. So in order to understand this day-to-day variability, we look at the geomagnetic condition in this period. So these red boxes are gold observation period. It's after sunset, it's nighttime. So the first day is happen to be at the initial phase of the solar storm. And the second day is during the recovery phase of the solar storm. And so if we want to understand the whole plasma density change, we look at O plus continuity equation. So the density is determined by transport by neutral wind, and the transport by E cross B drift, and the transport by ambipolar diffusion. And then also, of course, chemical production and chemical loss. And after sunset, there's a magnetic storm. So the neutral wind and the electric field both can be disturbed by the storm. And the ambient polar diffusion is a reactive forcing, so it's reactive to change in the forcing from the neutral wind transport, from E cross B transport, and also from chemical. And at night time, there's no more production, but there is still loss. And the loss is highly dependent on altitude. So this slide shows the physical process of the merge of the two plasma crest. So this is altitude versus latitude. This panel is transported by E cross B, and this lower one is transported by neutral wind. So you see both E cross B drift and the neutral wind transported downward, because you see this negative on the top. That's negative is meaning less. The blue color is less. The red color is increase density. And so I want to talk more about this E cross B drift. So here, this is better drawing, but this is a magnetic field. And so this is a downward transport of the E cross B. When it transports plasma downward, at the same time, it transports plasma towards the magnetic equator. So it's basically an opposite process of the fountain effect, which is during the day it creates the equatorial ionization anomaly that's too peak. About the magnetic equator. And also this downward transport to suppress plasma bubble formation. And the augmented effect of these two downward transport is make the plasma look like this distribution, the plasma distribution, altitude versus latitude. You see these two crests merged together. So this, I want to point out here, if you're looking at this, both the E cross B drift and the neutral wind can be very localized, and also it's very hemispheric symmetry. So because of this localized and asymmetry forcing, it can cause a very highly dynamic variation in both the plasma density and also plasma bubble formation, and therefore impact scintillation of GPS and high frequency radio signals. And this representing day-to-day space weather variability. And in this case, there's a storm, but even without storm during white time, this same process is still going on. Yes, so it is independent of the geomagnetic storm. And now move on to the annual and semi-annual variation in the IT system and the winter to summer meridional circulation in the lower thermosphere. So this is a annual semi-annual variation in neutral composition, which is also often measured by the ratio of the atomic oxygen to molecular nitrogen. And this is ON2 measured by time movie. So this representing each panel representing 4 days in 2007, and this is from time satellite, which the altitude is about 625 kilometers, has a high inclination. So each day there's like 15, 16 orbits. So this is from this orbits. And to the right, these 2 days representing the equinoxes, and this left side representing the solstices. So first you see semi-annual variation. Near the ON2 is larger near the equinoxes compared to the 2 solstices. And then there's the annual variation where the ON2 has a primary low near the June solstice and the secondary low near the December solstice. And this is a model data comparison of the composition, looking at just the equatorial region and the noon. And the blue is a TIGCM model simulation, and the black is a timed movie observation. And you see there's a discrepancy between model and the data. And the largest discrepancy is near the two solstices. The difference is at least like 50%. And this is compared the mass density with model data comparison of the mass density at satellite perigee, which is also about 400 kilometers. And the y-axis is a ratio model to data. So if it's 1, then the model is perfect. And each panel representing 1 satellite. And this is also the 5 years, the same period as this composite going to. So you see this also see a pattern of discrepancy in model and the data. And in this case, it's mostly near the June solstice. So this is same each year. And this year has also the December solstice. And it's pattern is very similar among the 5 sites. So we look at what causes this large discrepancy between TIGCM and the data. So first looking at the properly included forcing in TIGCM. So the first is the annual variation in sunburst distance, and that causes annual variation. And I think there's a semi-annual variation in thermosphere circulation. So during the solstice season, you have a large summer to winter interhemispheric circulation, and which is kind of mixing the atmosphere, just like a spoon, like stir coffee. So the atmosphere is well mixed. So you will have a larger mean molecular mass, and so you will have the smaller density scale height. So if you're looking at the Leo altitude, like 400 kilometers, you will see smaller density. And then there's a semi-annual variation in geomagnetic activity. So near the equinoxes, the geomagnetic activity tends to be so high because of the Earth's magnetic pole is like slanted, it's not like vertical. And which causes a geometry that is more favorable for the connection to happen. So therefore you will see stronger activity. And then there's inadequately represented forcing, and the NTIGCM, there's a free parameter called KZZ. And usually this KZZ is eddy diffusion, and it representing the turbulent transport of gas, heat, and momentum. But in TIGCM, because the TIGCM lower boundary is at 97 kilometers, so you have a lot of lower atmosphere forcing that cannot be properly included. And so the KZZ, not only this, but also KZZ is a constant with time. So clearly it can be very inadequate because the lower atmosphere forcing cannot be just constant with time. So this is what we work on. So this is a ratio between model and the data. One means it's perfect, and the black is a pattern of discrepancy. And so we do a Fourier fit to this pattern of discrepancy first, and then we do the model simulation sensitivity test to find a relationship between simulated neutral density and KZV. And based on these two information, we can get this solid red line. And then you do a Fourier fit to this solid red line. Then you get a KZZ parameterization, which you can put at the lower boundary of the TIGCM. And then now looking at model data comparison. So again, this mass density is blue is a constant eddy diffusion, and the red is a variable eddy diffusion. So you see significant improvement in mass density. And then the lower panel is ON2, and the black is UV observation, and blue is a constant eddy diffusion, and the red is the variable eddy diffusion. Again, you see significant improvement. And here I want to emphasize this terminology like eddy diffusion and KZV, because there might be some confusion in our community. The Jones et al. 2017, 2018 conducted a time GCM simulation and concluded that the eddy diffusion is not a primary driver of the IT semi-annual oscillation. So, however, I want to emphasize that KZZ in TIGCM is more than eddy diffusion, and it represents all the lower atmosphere forcing that is not included in TIGCM due to the lower boundary location. So I see this as a pure mathematical solution. Because KZZ is not really a physical process. So what is the physics? So for this, we look at meridional circulation in the atmosphere. So in the troposphere, we have 3 meridional circulation cells in each hemisphere. Moving into the stratosphere, there's a blue adoption circulation. And moving to the mesosphere, there's a summer to winter mesospheric residual circulation, and many of us are very familiar with this circulation. And then in the middle and upper thermosphere, there's also a summer to winter circulation that is driven by solar heating. And between these two summer to winter circulation, there's a winter to summer lower thermosphere residual circulation. And this is the circulation that we will focus on now. So again, this is a recirculation in the mesosphere and thermosphere. And so the lower thermosphere residual circulation is very shallow. And it's located in the altitude region of about 95 to 110 kilometers. So if it's shallow, it's about 15 kilometers. And it's a small event. The zonal mean meridional wind is only a few meters per second. And the vertical wind is only a few centimeters per second. So, and also it is located in this ionosphere region. So you can imagine it's very difficult to measure. However, if this circulation is true, is real, then between these three circulation, you will have these two convergence zone, which will transport the tracers and have high concentration of tracer in these two regions. So this, which we can see here in this slide, this is SABRE CO2 concentration from SABRE. And this is a vertical gradient, actually, vertical gradient CO2. And you see a high vertical gradient in this region. And it's in vacuum model simulation. And at the top is the vacuum model simulated recirculation. So this is a two convergence zone. So we based on vacuum model simulation, based on this magnitude of this lower thermosphere residual circulation, the V star, W star, and their latitudinal distribution. So basically, it's a climatology. We implemented a lower thermosphere residual circulation as the first two pressure level of the TI from the lower boundary in TI-GCM. And so here on the left is the comparison. The blue is the one with without this residual circulation. The red is when we impose this lower thermosphere residual circulation. And you see this in the winter hemisphere, the ON2 reduced by 39%. And this is very, very consistent with the recent high resolution WebMax model simulation. So this dotted line is regular resolution WebMax, and the solid line is 36. Solid line is the high resolution WebMax. You see the difference in ON2 is also reduced the winter hemisphere ON2, and the difference is 36%. So from TI-GCM tell us that this lower thermosphere circulation reduced the winter hemisphere ON2 by more than 30%. And this explains a long-standing issue of too much ON2 in the winter hemisphere in both of the TI-GCM and the regular resolution WebMax. And it's not only reduce the ON2, but also changes the, very importantly, it changes the latitudinal distribution of the ON2. And when we compare with the data, this is the top panel is a timed UV observation in January, and then the middle is the TI-GCM without the circulation. The bottom is the TI-GCM with the circulation. So you can see the latitudinal distribution of ON2 is much more consistent with the data. And then looking at the impact in the ionosphere. So the top is again the ON2, and the bottom is the electron density at F2 peak. So you can see the corresponding change. See the reduce of the plasma density in the winter hemisphere. And this is also a long-standing issue in long-standing wind from in both TI-GCM and WebMax model. We often see we have too much winter anomaly compared to data, for example, cosmic data. So so far I talked about a little bit of recap. I talked about the two modeling study. One is the KZZ parameterization, and the other is the winter to summer meridional circulation. And the top figure is the KZZ comparison, constant versus the variable for ON2. And the bottom is the one that when we have a lower thermosphere religious circulation versus without. So what's the connection between these two? So if you're looking at the x-axis, the top is looking at the entire year. The bottom is like January 30, 2007. So the bottom figure is looking at this point here, January 30. So we not only need to reduce the model simulated ON2, but also you need to get the latitudinal distribution correct, as shown in the movie observation. Because KZZ only varies with time, it does not have a latitudinal variation, and it's not really a physical quantity. And this lower thermosphere residual circulation is one of the missing physical process that was represented by the KZZ parameterization in TREGCM. And this circulation is thought to be driven by the momentum from the lower atmosphere wave, but we don't really know how exactly it is formed by this momentum deposition from the lower atmosphere wave. And so the understanding this seasonal scale variability is very important because it has a critical implication in the preconditioning of the IT system, important to how it responded to geomagnetic storm for both the plasma and the neutral density. So lastly, we're looking at the IT trend. So this is a altitude versus mass density percentage change in a 20-year period. The black is, this is global averages. Black is the total mass density change in these 20 years. And the green is by CO2. And these two are data points from long-term satellite drag data. And the red is the ozone, and the pink is the methane and the water vapor. So you see in the IT altitude, CO2 is the dominant forcing. And it causes a slow, steady cooling, which is in the order of -2% per decade. And this has reduced drag, essentially allow the space debris stay in orbit for longer, so it aggravates space debris accumulation. And so we know that CO2 causes a global warming in the troposphere. So why it causes cooling in the IT system? So the reason is because atmosphere density decreases exponentially as altitude increase. And in the troposphere on the left, the CO2 radiative transfer is in local thermodynamic equilibrium because of the collision between the CO2 and the O2 and the N2. And in the upper atmosphere here on the right-hand side, the collision is so infrequent. Therefore, the radiative process dominates. So the CO2 energies radiate away into space through infrared radiation. So it has a cooling effect. Now, looking at this the trends in the IT system, the contribution from CO2 versus slow drift of the Earth's magnetic pole. So on the left is a neutral and ion temperature at 300 kilometers, and it's in 1965. And the middle column shows the temperature change in a 50-year period due to CO2. Right column shows temperature change due to magnetic field drift. So as you can see, CO2 dominant over, over the magnetic field impact, and also the magnetic field trend cause both negative and positive temperature change. So when you do global average, it is very small. However, in the ionosphere, when you're looking at the ionosphere, in this latitude region, that's where the magnetic field inclination angle changes a lot because of the slow drift of the magnetic field. Therefore, it can, in the ionosphere, it can cause comparable trend in the ionosphere. So in summary, we're looking at solar flare. Solar flare causes very sudden irregularity in plasma and neutral density, impact GPS and high frequency radio signal propagation, satellite drag, and it has feedback in the magnetosphere, which impacts the energetic particle precipitation and electromagnetic energy flow from the magnetosphere to IT system, and the subsequent energy dissipation in the IT system. And we looked at last year, and we see that we discussed that the equals drift and the neutral wind can be very localized, and it is hemispherically asymmetry. And this causes a very highly dynamic variability in the nighttime ionosphere in plasma density and thermal bubbles, and which impact the scintillation of GPS and HF radio signal. And this representing day-to-day space weather variability that is independent of geomagnetic storm. And we looked at the residual circulation in the lower thermosphere, and it caused a large change in thermosphere ON2 and also plasma density. It explain two long-standing issues in TIPCM and wet mass model. And this signal scale variability has critical implication in terms of the preconditioning the IT system and for the storm response of both plasma and the neutral density. And for the IT trend, we're looking at CO2 trend. It's the dominant force in driving the slow and steady cooling of the IT system, aggravating the space debris accumulation issue. And the future study. So today we're mainly using a time scale as a theme to looking at the variability. And certainly all this variability has a spatial dimension, latitude, longitude, altitude. So when we're looking at a particular variability, we always ask ourselves two questions. Do we know this variability? And when we think about this, be very mindful about the temporal and the spatial scale of the variability. We also ask ourselves, do we understand this variability? We usually use a model to looking at the mechanism. So we need to think about is the model resolution and has the required resolution to looking at this mechanism. So I'm working on 3 ongoing projects. So first project is looking at hydrogen from its source region, which is the mesosphere, lower thermosphere region, produce. And then get transported to the thermosphere, and then goes to exosphere. And in the exosphere, it can go into the plasmasphere, and therefore go doing the charging reaction with the ring current, and therefore impact the magnetosphere and IT system coupling. And the second project is we're looking at the annular symmetry in the lower thermosphere visual circulation. And the third project is looking at nighttime localized electric field, neutral wind, and plasma drifts. And I'm also involved in preparing for the NASA GDC and the dynamic missions. And I'm on science team for GDC Mosaic instrument. And I'm on Daphne team for this A study for the dynamic mission. And the new solar and space physics decadal survey emphasizes system level understanding of the geospace and the coupling across the domain and across scales, and the predictability and the data model integration and the space weather and space climate impacts. So future direction in IT research, in my view, is looking at advanced system level understanding of the geospace and study the IT system within the context of the coupled Sun-Earth system, and emphasize cross-domain and cross-scale coupling, and leverage the ever-enhancing clean power, and to be able to do more high-resolution wave mass model, to be able to resolve more gravity wave and plasma bubble simulation, and improve whole geospace model, range model, and therefore improving the very critical aurora energy input for the IT system, and enhancing predictability through data model integration, leverage NCAR HAO's modeling strengths, and doing more data simulation and even machine learning, eventually towards a space weather forecast for society in the satellite tracking and position GNS navigation, HF communication, and space traffic and debris management. So this is my last slide. Thank you.
Okay, we have time for question. Anyone in the room or anyone online, you can just raise your hand or type into the chat.
Thanks. That was a great overview of all the ionosphere, thermosphere science.
Can
And
you introduce who you are
okay, I'm Tom Woods at University of Colorado.
from the same university?
Okay. And I work at LAS and worked with, timed and SDO modeling with flares in the time GCM and stuff
Great,
like that.
great.
So,
Yeah, I heard your name, never met you.
okay. Well, glad to meet you. Anyway, my question is, this is obviously a complex system with inputs from above and below. What's causing the largest uncertainty now in your models for being able to do better predictions?
I would say the largest uncertainty I would say the energy input from the magnetosphere, particle precipitation, and the convection. Not only in the how much the electromagnetic energy actually comes in, but also the pattern convection pattern. And this is a very large source. And just even if magnitude is good, the convection pattern is right, not right, it can cause big difference. So I think that's one source of large uncertainty. And another uncertainty is the lower atmosphere wave is coupling, because coupling with the lower atmosphere, it's so complicated, and it's cross scale, and it impacts the small cross scale, the small scale waves interact with each other and the interaction with the mean flow. So we have a lot that we don't know. Even like what I talked about in the lower atmosphere residual circulation, we still don't really know how it is going to change over the year. Yeah. So the coupling.
Go ahead, go ahead.
You go for it.
Well, I just, because we hear about the circulation, and I always wonder how good a handle we really have on that, other than the models, because usually the speeds are so low that it needs to be there to make things work, apparently. But do you measuring it? Is it the actual measurements or actual data that shows you this? I mean, how much is there that really shows you that? I mean, maybe at low altitudes you have it, but higher altitudes, some of this is supposed to be still happening. And okay, so it's below the threshold of our instruments.
Okay, so can I ask a question, which will partially answer your question? But
Okay.
then I have more questions for Ian. Okay.
Shinzo is very excited about.
Yes, yeah. First, I say, Ian, you did a great job. It was really nice, very impressive. I didn't know much of your work, but this talk gave me a very good impression on that.
Thank you.
So I was also very interested in her finding. Not finding. You were not the first. Han Yi, when we devised Chihoko and Botan, we saw that winter to summer circulation in our atmosphere. But you did a very comprehensive study. So that may help to explain my measurements from McMurdo Station in Antarctica. Because I had the results already like 4, 5, 6 years. I didn't dare to publish that. Because
typical.
I shoot a beam exactly vertical. So I measure vertical wind only. And over the years, whenever, it's in the winter time, May, June, July, August, these when I can have nighttime measurements, my vertical wind is not just one, profile nearly zero. It's tilted. Below about 90, 95 kilometer is a downward wind. And above that is upward wind. Very similar to your slide, which one? 28, 29? The one you have a drawing of that. Yes.
That one.
Yeah. So for that one, if I'm on the winter side, you will see it's downward below certain altitude, go upward above certain altitude. And my measurements, the altitude range, the sign, they all consistent with these. But the reason I didn't dare to publish the paper is I'm on the meter per second magnitude, not a centimeter per second. But of course, you were saying centimeter per second, that's zonal mean.
Zonal mean, yes.
So I need you to check for me if you go to your next one. Yes, you have this January. Can you check for me for July?
Yes.
I need it not to be zonal mean.
Yeah. And then remember, this is also zonal mean, you know, this is zonal mean. It's a residual circulation.
Yeah, and also for many years of average.
Yes, it's a climatology. So for you are at a fixed location.
Mm.
So we need to looking at probably need a high resolution like max, and looking at that particular location where its instrument is.
Yeah.
And I think you should be able to see. Very likely you would be able to see much larger vertical wind.
Okay.
Yeah.
I hope so. So I can't tell you about lower to, I mean, the middle one.
Well, but how high do you go?
How high I go? I can go to 110 and even
Okay.
above. And of course, if I want waves, I go very high resolution. I go lower, a little bit lower altitude. But if I can sacrifice resolutions, then just to say, look at what's the mean background. We can go maybe 115, 120 kilometer. That's for the current system. If we can build the bigger ones, of course, we can do better.
Well, this is a simple experimentalist problem, right? You don't believe your data, and if you're a modeler, you don't believe your model. So,
Yeah. But now it's just the matter that wind. Later on, I checked all the temperature, sodium, iron, layer, density, shape, altitude. They are all self-consistent. The only thing is I'm on the meter per second scale.
yeah, so
Now
it's small. And so like, okay, is this
centimeter.
real? If I got
Yeah.
have I got a bias in my instrument somehow that's causing me to have a bias to of a meter per second?
Yeah, but I tried. It's not possible. I can have a artifact.
It takes a while to get there, though.
Yeah.
Is my-
So my question to you, go back to this previous one. So as you said, this I agree with you. This summer to winter circulation in the mesosphere is gravity wave driven, right? Pretty much wave dynamics driven.
It's wave, but I think tides is also involved.
Okay.
And we needed to find out whether it's a resolved scale wave or it's like a dissipation from dissipation. Because I know there was a recent paper written by Jack Wang of the CCMC. He looked at the mechanism, how it is formed, and his conclusion is like it's more from the resolved waves.
Okay.
And there's with some smaller contribution from subscale to dissipation.
That middle thermosphere, summer to winter
Yes.
circulation is solar heating driven.
Yes, this one is sort of heating driven.
So now we know there is a winter to summer
Mhm.
circulation in the lower thermosphere. To your idea, what's the mechanism? It's wave driven, or it's solar heating driven, or combination of them?
I think based on the altitude of this circulation, the altitude is like 95 to 110. I think it is definitely from low atmosphere wave, the momentum from low atmosphere wave. It's not locally driven, locally generated wave just because of its altitude. And usually people used to think this is from the dissipation of gravity waves. This with highest gravity wave, they dissipate at this higher altitude. And also tides dissipating this altitude because of ion drag. But Jack Wang recently wrote a paper. It says it's more from resolved scale wave. So my conclusion is we don't fully understand. So
I agree. So we need more research, right?
research.
It's
More research.
Proposal opportunity.
Yes. And I think I just want to go back to the first Tom's question. Another uncertainty is certainly solar irradiance. Solar irradiance because, for example, I particularly want to talk about this XUV. Even today, this we in our model, the irradiance, we always don't have enough electron density. And so we don't really have data, right, in that XUV. That is, it's only broadband data. We don't have like resolved, high resolution data. XUV is like a 0 to, let's say, 0 to 27 with them. We don't have very good data. And then, so that really impact that region, E region. So that is also another certain, yeah.
Okay, thanks.
Mhm.
Any question from
More
online?
discussion.
Oh, that's enough.
Okay.
You're not through yet, huh?
So for this prediction of the ionosphere, thermosphere for kind of space weather operations and stuff, what are you capable of doing now? And what is the requirement? How many days out in the future do you need a prediction?
I think that ours, like our only space weather predictions, like NOAA's posted space weather prediction center, and I know they use like WAM model. They do give prediction, and I think the prediction is not very good because I think it's because of lack of data. In terms of your question is like how many days in advance? Of course, even like 1 day, like even 1 day, 2 day advance, that would be great. Like I know, like for example, the gold one to observe the solar flare, and it take like 2 days to prepare for that. So if you can like a 2 days prediction of solar flare, that would be great. But we don't have that. So today's space weather is we are at like a infancy. So we don't really have good space weather prediction. Even from NOAA space weather predictions, it's not really. Yeah, I would say it's a lot of work to do.
From the Air Force, satellite drag community,
Oh, that was.
and also, of course, NOAA space weather predictions. They have expectations or requirements for these predictions. What about satellite drag? Do they have a need for prediction out for a week or a month or?
I think the answer that those guys will give you is the longer, the better.
Mm.
But, at this point, if you just give us tomorrow, it would be a big help.
Actually, what the saying usually was is, if you can get it right now, you're doing really well.
Yeah. Well, actually, they have trouble with that.
Yeah,
I mean,
the nowcasts are not good.
The Air Force has their own system, like has them data assimilation and has them model is not. So I think they previewed his satellite catalog. That has the model they use to assimilate data, and it is not open to the research community. Yeah. It's a different system.
yeah, because there's two problems. One of them is getting the models right. If you have the right inputs, the other one is getting all the inputs right. So,
And not having enough inputs.
and not having enough inputs. So there's two pieces. So the modeling is a lot to do and the inputs there's a lot to do. So, all right, between the two of them.
Well, what Frank Marcos showed was that your nowcasts improve tremendously if you have dedicated satellites to tell you the density at the moment.
Right.
Yeah, so we really don't have data. We don't have a good amount of data to do good data estimation. Honestly, yeah.
Temperatures are actually,
Uh,
the temperatures hold a lot of promise, I will say. It's not just my self-interest, but, some of the people on the team have done some work on the atmospheric temperatures. For drag, it seems to make a big, if you get the temperatures right, you have a big handle on the drag. But, it's not a commonly available measurement, right?
Can I ask another question?
Unless
Sure.
Yeah, because related to what you were saying, the temperature. Can you go to, I think it's page 26?
Page when?
26.
Actually,
Yeah. Oh, okay, don't move. Yeah, that's just that one. Okay, so about this SAO in the atmospheric density
Mhm.
variations.
Mhm.
So that Jones paper kind of like list different things, and Dr. Tim Furrell's paper list different things. And you later on, you and Yue also have Yue Jia.
Mhm.
Yeah, you guys have this. So I want to ask your opinion. There's a temperature changes could cause density change. There's a composition change could cause density change.
Mhm.
And there's these circulation change could cause change. What's your opinion on these?
Yes.
What's their quantitative contributions?
Yeah, the neutral density is determined by temperature and the composition in O and two things. Yeah, so the circulation change usually mostly change O and the composition,
Mm.
and therefore change the density. The temperature changes the neutral density at fixed altitude.
But circulation change can also cause temperature change.
Yes, but that's by comparison, does not, we didn't really quantify this too, but we always looked at the composition. Yeah, when you have downwelling, you do have a compression, heat, adiabatic heating.
So Wenbin, you have some input?
No, what I'm saying is that circulation two effects. One is the temperature,
Temperature.
and then is the composition.
Yeah.
The neutral density mostly responds to temperature. That is what the circulation indirectly affect neutral density, not directly.
Yeah, so basically looking at the scale height, H equal KT over mg, right? T, so T is there.
Yeah.
And M is the mean molecular mass. So earlier we talked about spoon mechanism, mixing that to increase M. Yeah,
Decrease scale height.
yeah, so that decrease scale height. Therefore, when you're looking at the 400 at fixed altitude, you will have less density if you have a larger mean molecular mass. Yeah, and you increase temperature, you increase the density scale height. So if you're looking at if you increase temperature, then the density at 400 kilometers, when you're looking at the fixed altitude, the density will be larger. So it's this looking at the scale height. Yeah.
Thank you.
I actually have one last question, if
Okay.
I may. The lower thermosphere circulation, you talk about how it changed the sort of winter hemisphere
Right.
composition. Does it also sort of mostly address this sort of global scale seasonal variation?
Yes.
Okay.
Yes. Yes. I wanted to look at it. So one definitely changing this, looking at the two solstices, and even they are different. Like in the mass density, you see December solstice. Actually, the model is doing okay. It's only the June solstice, and for the composition, it seems that December solstice is also discrepancy. So that's why I want to look at this N asymmetry in this lower hemisphere residual circulation. How different they are, June solstice versus December.
Any last question? If not, thank you again.